Hello everyone. Welcome to the TIFR CAM Colloquium. And I would like to introduce Professor Ron Peled from the Tel Aviv University, who will be telling us about random packings and liquid crystals. Over to you, Ron.
All right. Thank you very much, Nishant, for this invitation, and thank you all for joining. So don't be intimidated by the physics words. I will try to give an interesting meaning to everything. And moreover, this is a picture talk, so I think it should be enjoyable to watch interesting pictures and hopefully to understand the physical phenomena. So please feel free to ask any questions that you have. Throughout the talk, I use pictures that are not always prepared by me, so I've also written where they're taken from. Okay, so what do we see in these pictures before we go into the talk? This is to give some idea of these words of random packings that appear in the title. Here, for instance, you see packing of balls in 3 dimensions. And well, I haven't explained what the word random here means. So how are these balls picked and how are they put exactly in these locations? But you can have in mind that randomly putting balls in a domain may have given a picture like that. Here you see something similar, but now the basic object that is being packed is not a ball, but rather this kind of rod here. You see these long rods. And then you see 2 different types of packings, one which seems disordered and one in which the rods are going in one direction. Here again, you see something else. Here the basic object is a square, a 2x2 square. And these squares all have their centers on the lattice. So this is very different because all the centers of everything is on the lattice like that. Okay, so this is the basic objects. And now let's go into definitions here. And the portions of this talk will be joined with Daniel Adas, my student at Tel Aviv. Okay, so what we're actually going to study is the so-called hardcore model. So this is one way to make rigorous this idea of a random packing. So what is a hardcore model? So it's a probability distribution on the ways in which you can place non-overlapping copies of some tile in a domain, like we saw just now. Maybe your tile is a ball, like here. Maybe your tile is a cube. Maybe your tile is on the lattice somehow, and it's like a rod on a lattice, and so on. So generally speaking, you're given some tile, a T, a subset of RD. Maybe you also allow some of its rotations, like we see in this picture at the bottom here, or maybe you don't allow. And then a configuration. This is a way to place the tiles. This is a non-overlapping translations of this tile T, maybe with the rotations of it. Sometimes I work on a lattice, and sometimes I work in the continuum. If I work in the continuum, then the translations are any translations in RD. So you can move your ball, say, to have any center. But if I work on a lattice, then it means that your translations are taken from this lattice. So the center of your tile must be on a lattice. So you can either do this or that, and people study both cases. Now, I'd like to tell you how you actually make this probability measure. What is this probability distribution that I'm referring to? So how do you randomly sample a configuration? How do you decide where to place the tiles? And the most natural thing you might want to do is to say, well, I have a certain domain, and I'm just going to place a certain number of my tiles in the domain uniformly. What does uniformly mean? Uniformly, if you're in RD, means according to Lebesgue measure. If you want to place 5 tiles, then you look at all the possibilities to place the 5 tiles, and you, according to Lebesgue measure, you sample from this 5-dimensional space, so to speak, putting tiles in a bounded domain. So you have Lebesgue measure. If you're on the lattice, it's even simpler. You just have finitely many possibilities where to place these non-overlapping tiles, and you sample uniformly. Now, this is the most natural thing to do, maybe, And if you do that, then I say you've fixed the density. But usually we do something a bit different, which is supposedly equivalent. Usually it's equivalent. So this is the difference in physics between canonical and grand canonical ensemble. Usually we don't quite fix the number of tiles. Instead, we fix something called a Fugacity parameter. Fugacity will control the number of tiles. So small fugacity will mean that you have few tiles, dilute configuration, not quite few, but few. The ratio of the number of tiles to the maximal possible number of tiles will be small. And large lambda will mean that you have almost the maximal density. And then the measure that we actually put is this mu lambda measure here. So let me explain it on ZD. Suppose you are working in a domain lambda of ZD, and you want to see a certain configuration sigma, then the probability that you will see sigma is proportional to lambda to the number of tiles in of sigma. So again, if I, just to explain this measure a bit better, if I were to condition in this measure on the number of tiles that I see, then the distribution would be uniform over all placements of this tile. But what is still random is the number of tiles. And I'm going to sample the number of tiles according to this lambda to the number of tiles in sigma times the volume of possibilities for that number of tiles. So it's like a two-step process where I first sample how many tiles there will be, and then I sample the uniformly among all choices of these tiles. And when lambda is small, I have a small density of tiles. When lambda is large, I have a large density of tiles. You don't have to understand this in all detail, but this construction, which is slightly more involved than just picking uniformly from a fixed number of tiles, is very convenient in practice. It is very natural in many points of view, and it is the standard measure that people put on these kind of objects. So this is the probability measure that we would like to study. Again, the basic object is what is your tile. And by the way, I've written here or molecule because this could be like a material, and this could be like a basic atom of your material. And then it naturally relates to the question of what is the interior structure of the molecules of a material. We will see some pictures. In any case, you want to know what's your tile and whether you're working in RD or ZD, and the rest is the standard prescription here. So let's see an example, and that might help a bit. Okay, and just what are the questions that we study? If you have a low density of tiles or small fugacity, then usually the tiles hardly interact. There is one tile here, one tile there, one tile there, but the fact that they are non-overlapping is not very, it's not a strong constraint on the system. And then tiles are mostly isolated, and we say the system is disordered. For instance, if you know whether there is a tile in one corner, it hardly affects the probability of having a tile in a different corner. So somehow fast decay of correlations. But the main questions we would like to understand is whether when you start to put more and more tiles into your domain, when the system gets very, very constrained because there is a very high density of tiles, do the tiles take on a specific order? Do they locate themselves in specific positions in order to have more and more possibilities for how to put them? So let's see an example. So this is the most classical and perhaps also one of the simplest examples of this model. It's the nearest neighbor hardcore model on ZT. So here the tile is going to be this little circle here. And the center of the tile is going to be on the lattice, on, in this case, the square lattice in this picture. So we're going to place tiles on the square lattice. And the way this tile is chosen is such that if a certain center is occupied, then it means that the neighboring centers cannot be occupied, because otherwise they will overlap. So the exclusion is between a point and its neighbors. Adjacent point cannot be occupied, but other than that, everything is possible. And this is also interesting in combinatorics. It means you have an independent set in this graph, in this square. So we want to study how does a packing like that look like. And again, if you have a small density, then you see there are some, mostly tiles are just appearing in single clusters of size 1. Sometimes you see 2 tiles near each other, but they're mostly non-interacting. So you may imagine that there's not much order in this system. If I tell you that there is a tile at one corner, say, you learn hardly anything about the other corner. There are many ways in the mathematical literature to make this idea precise. I've just used here the word disordered, but there are more precise meanings that I'm not going to get into. Like you can use the Dobrushin uniqueness theorem or Vandenberg's disagreement percolation method or cluster expansion. And you learn in particular that there is a unique Gibbs measure. I don't want to enter into these more technical definitions, but you get the picture, I hope. Now, what we would like to study instead is what happens when lambda is very large. And when lambda is very large, it means that you're packing almost the maximal number, the maximal possible number of tiles in your domain. And then it makes sense, before you want to study what happens when you have, say, 99% of the maximal number of tiles, you might want to study what happens when you have 100% of the maximal number. So when you have really the maximal packing, because at least heuristically, it makes sense that the maximal packing and an almost maximal packing might be similar. So when you want to study the regime of large lambda, you might be interested in what happens for lambda sort of equal infinity, the maximal density. And it's very easy to convince yourself that in this model, because of the bipartite structure of ZD, there are exactly 2 maximal packings. They're both periodic also. You can either occupy all the even centers, the centers with the even sum of coordinates, or you can occupy all the odd centers. And in this way, you get the maximal number of tiles in your domain. So, so this is what happens in the maximal packing. And what Dobrushin proved, one of the first mathematical theorems in this field, is that indeed, when lambda is large, not infinite, but large, then a typical packing looks very much like the maximal density packing. It will coincide either with the even occupied packing or the odd occupied packing at 99% of the positions. There will be a few centers which are missing, and sometimes there will be a few centers which are taking the wrong parity. But in most positions, you take the same parity as the maximal density. And I will show something about the proof of this, because in these talks, it's good to have at least one proof, and you will see more precisely what they might mean. But again, this is the behavior at large lambda. So what we see, we say that there is a phase transition in this system. At small lambda, the system does not exhibit any order. If I know something about what happens in the system here, I learn hardly anything about what's happening here. But if I'm at large lambda, it's not the case. If I see that there is a tile here, then I can learn that probably it's the even tiles which are occupied, and then I can deduce that probably here it will also be the even tiles. So you can make several mathematical meanings to these statements, but in particular, the model has what we call 2 Gibbs measures, 2 periodic. So I'm not getting exactly into the technicality. Let me just mention some open questions about this before I say something about the proof. Even in this simple model, the simplest, almost the simplest of all these models, we don't know that there is a single lambda where the model transitions from the first type of behavior to the other. So it's very, very natural that as you increase the fugacity, the model goes from being disordered to ordered. But we cannot rule out that it is disordered, ordered, again disordered, again ordered, again disordered, again ordered for a while, until finally it fixates on being ordered. So we don't know that there is a single transition value. And another question that I was personally involved in, we don't know whether the transition from disorder to order, assuming, say, that there is a unique value, what is more or less the magnitude of this critical fugacity? We know it goes to 0 as a power law with the dimension, but we don't know the power. So this is some understanding of the dimension dependence. Let me give some sort of picture hint to this theorem of the Brushin, just to give you a flavor and to give at least one proof in our talk today. You see my pictures, right? Yes, very good. So what do we see in this picture? This picture depicts a particular sample, a particular way of putting the balls in the domain. But notice I've put boundary conditions. So the balls on the boundary are fixed. You cannot move the balls on the boundary, and it's only the balls in the interior that the configuration modifies. So this you can, in the notation used in my first slide, you can just say the domain has a few less options on the boundary. Now, what we see in this picture is that the boundary has only circle occupied. So circle means, say, even, the positions with the even coordinates. But here in the center, there is somebody who's occupied and is odd. So this center is not respecting the parity of the boundary. I want to show that this is unlikely. So the theorem of the Brushin, one way to phrase it, is that if you work in a domain which has all the even points on the boundary occupied, then the center is also likely to be even occupied. And here we see a violation of that. So I want to show that the event that we see in this picture, where the center is odd and occupied, this is unlikely at high fugacity. So suppose this happens, what should I do? I can look at other odd occupied sites, for instance, this one, this one, this one, which are adjacent to this center. Maybe I'll have to look a bit further because this one is actually adjacent to distance 2 to that. So I add a few, and in this way, I sort of explore the odd occupied connected component, if you will. So I'm exploring adjacent regions to the starting point, which are odd and occupied. And this naturally leads me to a certain boundary. What is this boundary? This boundary is a boundary between a region which is odd occupied and a region which is even occupied. So you can convince yourself with not much difficulty that if the center was odd and occupied, then there will necessarily exist such a boundary between region which is odd occupied and even occupied, because the boundary is even occupied. So this interface must exist. And now, what does the Brushin say? When you locate this interface, you can make the following crucial shift transformation, a very interesting transformation and useful one, using the discrete symmetry between the two maximal vacuums. You can move the configuration. Notice I've inside the interface, the region which is odd occupied, I shift it by 1 to the left. What has been gained by this operation? Now what was previously odd occupied becomes even occupied. You may convince yourself that this is always another legal configuration, that there's no overlap of the tiles by this operation. Sorry, like that. And what was gained? What was gained is that on the right boundary, all of these even locations are now free. Now you can, if you wish, occupy them with additional tiles. So what have I shown to you? That by moving inside this, this region, the tiles to the left, I've gained a lot of freedom to place additional tiles. And if I'm at a very high fugacity, then this freedom to add additional tiles means that configurations like this are more likely than configurations that we saw before, because they have more possibilities for tiles, and my fugacity is very, very high. So the final configuration is, well, the final picture is this, and it just tells you that these kind of configurations are more likely. So altogether, the conclusion is that it is unlikely that the center was odd occupied, because if it was, then there would be many other configurations, exactly these ones, which have many more tiles than it. This is an idea. I'm not going into technical details in this talk. I hope you got some gist of this idea. And this is a version of the so-called Pyre's argument in statistical physics, but adapted to this interesting and non-trivial case by Dobrushin. Okay, so this is what I wanted to say about this simplest example. Now recall, my interest is to study the high density or high fugacity, or sometimes the intermediate fugacity regime. In this simplest of all examples, we have gained an understanding. In the high density regime, the tiles would look like the maximal tacking. So we can say maybe that's always the case. Maybe no matter which tile you give me, the prescription to understand the behavior is the following. At high density, consider what is the maximal density packings, and what you will see is a small perturbation of that. That's reasonable. So let me tell you that sometimes other behaviors can happen, and this is the what is in my next slide. First, there is this funny so-called monomer dimer model, a basic model as well in the field. Here, the tiles are the edges of ZD. So you see that the tiles are just edges. Again, this is a perfect, and not a perfect, this is a matching in combinatorial terms. So it's also interesting for combinatorialists. What Hillman and Lieb proved in the 70s, later with an alternative proof of Vandenberg in 99, is that this model is disordered at all fugacities. In some sense, the reason for that is that if you want to look at the maximal density packings, then there are really a lot of them. This is like dominoes. This is dominoes on a square lattice. And if you want to pack dominoes on a square lattice, you have a lot of freedom. This freedom is so high that, that the model happens not to have any order at any lambda. This is a very strong fact, very interesting fact. So we see already that this is a different behavior. It is not like the behavior of the Dobrushin. Now let me show you that even more interesting things can happen. I will not show it, but I will give some interesting pictures. So let's try to understand what these pictures depict. I'm going to talk now about states of matter, not really in detail, but some idea. So you may have heard of liquids and gases and crystals or solids, but there is also another state of matter, maybe you haven't heard of that. It's called liquid crystals. A liquid crystal is a state of matter that is in between liquids and crystals. Let me try to give some idea of what this is about. A liquid or a gas, I'm not going to distinguish them in this explanation now, is what you see in this picture. So it's molecules which are somehow disordered. In what way are they disordered? Maybe you have a random distribution of how they're located, but what's important for me is that this distribution is invariant under rotating the space and also under translating the space. So if you look at this left-hand picture and you move it to the left or you rotate it, then it looks the same in distribution somehow. It doesn't look exactly the same, but there was no preferred orientation of the rods. There was no preferred translation of the rods. So it looks basically the same, invariant in distribution. This is what it would be to mean to be a liquid or a gas. This is the disordered phase. On the other hand, a crystal, this is like what we saw in the Dobrushin's proof. In a crystal, every tile has its own specific important position. So only the even sites in the Dobrushin's model were occupied. If you move this a little bit, then it will be different. Maybe the odd tiles will be occupied. That's a different packing. If you cannot rotate it, it was on a lattice, but okay, in that case, if you rotate 90 degrees, it will be still the same, but more generally, it might not be. So a crystal, you should think about a crystal as something which is invariant only under discrete subgroups of rotations and translations. And now, what are liquid crystals? these are somehow intermediate between liquids and crystals. For instance, and they come the typical the usual categories that they're cataloged under, and then there are many subcategories, are nematic, smectic, and columnar. So let me explain these categories. A nematic material is one where the molecules do have a preferred orientation. So if you rotate the material, it will be different, but they do not have a preferred translation. So these are like probability measures on packings, such that maybe infinite packings, maybe packings in the infinite space, such that if you rotate them, you get a different distribution. But if you move them to the right or left, then they look the same. Unlike in the Brushin's case, that you moved and they even became the odd, it was different. So they have a broken rotation symmetry, but a preserved translation symmetry. Okay? A smectic material, like in this picture, means that it comes in layers. In each layer, the molecules have a preferred orientation, but the layers are clearly distinguished. So if you try to translate this material up or down, then you change the layer structure. You move it by half a layer. If you move it by half a layer, it's a different thing. So we say the translation symmetry has been broken in the up-down direction, but it isn't broken in the right-left direction. The right-left, it looks pretty much like this nematic material. So this one has the translation symmetry broken only in a single direction, just up-down. And there are two directions, the right-left and the in-out directions, where it is invariant in distribution. And lastly, a columnar material is one in which, like in this picture, you have a broken rotation symmetry. So again, it's you definitely see a preferred orientation here. The disks go up, but and you also see kind of a lattice structure, a crystal structure, because the location of these piles, they form a crystal or a lattice. So the translation symmetry was broken in the right-left direction and the in-out direction, but it is not broken up or down, because actually these columns, if you look more closely, they have some gaps, and up-down, if you move things, they just remain the same. This is some idea. So again, it's a probability measure on packings, which will be different if you rotate it, will be different if you move it right, left, or in-out, but will not be different if you move it up or down. This is slightly more formal definition. Maybe is not yet quite formal. In any case, these are other states of matter. If you've never seen them before, I think they're quite interesting just to ponder this idea that there may be packings which display partial order, that some of the translational symmetry remains, but some is broken. So this is an interesting state of matter with a lot of uses in the sciences. Let me say something about how such states of matter might arise in the models that we're interested in. So we're looking at hardcore models. Let me say about what is the relationship between hardcore model and that.
So Ron, can I ask a question?
Sure.
So usually when I think of liquid phase or say gaseous or so then I'm thinking in terms of entropy, and here you're thinking in terms of symmetry. Are these at least somewhat equivalent in your at least in the cases that you have seen, or
I don't know why you think in terms of entropy. Usually when I think of liquid or gas, I think maybe in terms of correlation decay. Maybe a gas has exponential decay of correlation, liquid maybe has only power law decay, things like that.
Okay.
I don't know, when you say entropy here, here there's pressure because there's this lambda to the number of tiles. Sure. Here, if you fix the number of tiles, then you just are always looking at the maximal entropy packing because we're uniformly sampling. So I'm not quite sure what you mean by that. So it could be that the uniform sample will bring us to a nematic phase, could be a smectic phase, columnar, crystal. Everything is possible here.
Okay.
Depending on the density, the shape, the domain. the parameters of the system.
Now that we have taken a break, can I also ask a question?
Yes, please.
So could you go to the previous slide, please?
Yes. Do you mean the picture proof of the Brushin or just?
No, actually no. So that was a separate, I think that was not in these slides. So when you were basically showing the boundary was fixed at even positions.
Yes.
So the probability of having such a different disorder rather, that is the boundary is fixed at zeros, and the chance that I actually will have a configuration or a circle or a disk at a cross, that would depend on the size of the box also, right?
So maybe I didn't quite understand the question. Are you asking what's the chance that I will see this type of boundary condition?
No, the boundary is fixed, let's say.
Okay.
And then I want to see whether a disk,
whether the center
exactly
the center is odd, what's the chance to see that it is occupied?
Right.
So what is interesting in the high fugacity phase, and this is eventually what can be proved by this method, is that the probability that the center is occupied and is odd and occupied under even boundary conditions like that, this probability is small, irrespective of the size of the domain. So this is a very interesting phenomenon that no matter how large the domain, and the only thing you change this fixing the boundary of the domain, but still fixing the boundary of the domain at high fugacity will modify the system all the way to its interior, no matter how large, even somehow in the limit of being infinite, still mostly the even points will be occupied.
Yeah, so my question was as a function of the fugacity parameter.
Yes.
And the size. So now you basically answered that question in the sense like when the fugacity is very high, there is very high correlation structure.
Yes.
Very strong dependence. So therefore, it would permeate here. I understand. Yes. Thank you.
Would be uniform in the size. This is the phenomena of long range order. This is this crystalline structure.
I see. Okay. Thank you.
Sure. Please feel free to ask more questions. Okay, so I've explained this liquid crystal, I've given at least pictures. Let me say how it relates to the model that we're looking at, this hardcore model. So I will say just a few words about it. I will not have time to go into much detail, but here is the beginning of this, I think. I'm not fully an expert. Maybe there were previous, certainly liquid crystals were known before, but I think this made this connection to a hardcore model. So Onzager, famous chemist, who also got the Nobel Prize, studied the packing of long rods in 3 dimensions, as you see in this picture. He predicted, that is, he gave an argument, but it's not a mathematical argument, that there will be nematic order, meaning that the rods align in the same direction at intermediate densities. Align in the same direction, but they don't have a crystal structure, so they're still somehow the invariance to translation is preserved. And this remains unproven mathematically. So somehow the idea is that if you take your domain and you put more and more rods into it, each time you uniformly sample a packing with this many rods, then eventually it's better for the system to align the rods in the same direction, because then they will interfere with each other less, and there will be room, more freedom, more entropy to put more of these rods. So it's easier for the system to put more rods if they're aligned. This was the prediction of Onzager, at least at intermediate density values. This is still unproven, but there has been mathematical progress and also many physics studies. Here, I should mention very important contributions of Deepak Dar and the co-authors, Shah and Rajesh and others who have studied these models and have published quite a lot on them. There has been proofs of nematic phases in other models, hardcore models of a sort, but of various types. With rods of different lengths, polydispersed means different lengths. on the square lattice, rods of a fixed length on the square lattice. This is what is depicted here. And also for so-called interacting dimers, anisotropic plates by several authors. Yoffe Velenik Zoradnik, the Sertori Giuliani, Jocelyn, Hillman, Lieb, and maybe these are some of the main works from recent years on nematic phases. Let me explain what they've found, for instance, in this. This is not what is proven in the Sertori Giuliani. They only talk about the intermediate phase, but let me explain the predictions. So the predictions, for instance, for rods of length 7 on the lattice is that, well, again, if you have a low density of rods, then they are non-interacting, again, as before. What you see in one corner of the domain hardly impacts the other corner, say. On the other hand, if you increase the density, then the rods find it preferable to mostly orient in the same direction. So if you see on this corner that they're horizontal, then you're very likely to also see it in that corner, say. So there is long-range order. But it's a nematic order, meaning that the rods prefer to be horizontal, but they don't have a preferred translation. If you shift this to the left or right, or up or down, it looks basically the same. So this is a nematic order. Another interesting fact is that later, if you increase the density even more, then the rods no longer have a preferred orientation. This phase, called the HDD phase by Shah, Dar, and Rajes, is not well understood, I think, not fully understood. But what is interesting is that suddenly the rods lose their orientational. You can get some idea of why that happens if you try to think about maximal density packings. In a maximal density packing, it would be preferable for rods to align, and moreover, to all have the same starting and ending point. So maybe they completely fill a square like that, if you have very, very high fugacity. But if they completely fill a square, then nothing prevents the rods from changing the orientation to a vertical one. And indeed, if many squares are like that, then you would gain entropy by changing half of the squares to vertical and half of the squares to horizontal. And I think this kind of change is the driving mechanism to the fact that at very high fugacity, the rods no longer have a preferred orientation. At intermediate densities, you don't tend to fill a square, and then the driving mechanism is the fact that the rods want to keep their translational entropy. So they don't want to exactly fill a square, but instead they want to exit a bit from the right or left of the square, and then that interferes with the ordering of the adjacent squares and causes the whole system to order in the same direction. So this some idea of why this is happening, but in any case, it's a very interesting picture that you have two phase transitions, and then this last phase is not so well understood. And the intermediate phase was given a rigorous mathematical proof by the Sertori and Giuliani, at least when the rods are long enough. Okay, let me go on.
I'm Madhusudan. I just wanted to tell that, you see, these problems arise only if you have non-interacting particles. The moment you introduce interactions, that is, intermolecular interactions, the picture changes, especially in 3 dimensions.
It could change, that's right.
And there is no problem in having a nematic liquid crystal display, for example, working extremely well, even at high densities.
That's right, so definitely. If you add interaction to the tiles so that the tiles attract each other or repel each other, or have, if one is horizontal, the adjacent one also wants to be horizontal. If you add such forces, then you can push the system into a certain order, which might not have been present if you didn't have the interaction. For instance, this was the driving mechanism in Hillman-Lieb and Jocelyn-Lieb. I said in a previous slide that when you have simply the monomer dimer model, then it's always disordered. But they proved that if you add to that a certain interaction, then you can make it nematically ordered. So exactly as you say, if you add interaction, you can change. But for the simplicity and also maybe mathematical beauty, I'm only discussing the model without interaction. And yeah, you can definitely widen the scope and add interaction.
Yeah, that's
Very good.
okay.
Also, if you think about links to combinatorics, for instance, then maybe it's very natural, more natural to just think of a independent set or uniformly sampled set and not add interaction. But anyway, it's these both are important. So we move on. Arguably, the most natural model would be to pack balls in RD. What is known about that? As you can see in this picture, it is predicted that there is a crystal order at high fugacity. So if you place enough balls, then probably you're just going to see one of these densest lattice packings at high fugacity in dimension 3. At high fugacity, but the physicists predict that this will happen in 3 and higher maybe dimensions, 3 dimensions at least. But in 2 dimensions, it's predicted that you only have nematic order, but it's not going to look exactly like the triangular lattice everywhere, but rather there will be invariance to shifts. That's an interesting prediction related to the so-called Mermin-Wagner theorem in statistical physics, but I won't have time to get into that. Let me just say that this is completely unproven mathematically. The difficulty is, and this was also the difficulty with the long rods that I presented earlier, is that we don't know how to show that the continuous symmetry, the rotational symmetry is continuous, and sometimes the translational symmetry also is continuous. We don't know how to show that that continuous symmetries are broken. On a lattice, it's much easier. So somehow the fact that we are allowing all the rotation, that we work in RD, and then this is a rotationally symmetric tile, is really hindering the mathematical progress, and this is a very important problem to understand. There's really the 2 main results that do exist is that in 2 dimensions, there is no translational order, so it's almost the nematic order, but we don't know that the rotational symmetry is broken, and that that if you want nearly touching balls, then these will form an infinite cluster at sufficiently high fugacity. So these are 2 important results, but generally the picture is very, very far from mathematically established. So I've just touched upon this packing of balls. And finally, in my last few minutes, let me tell something that is related to my own recent work. First, I tell of the work of Mazel, Shtul, and Sukhov. Mazel, Shtul, and Sukhov, I think their motivation may have been the packing of balls, but in order to approach that, they said, let us take a lattice approximation. What does it mean to take a lattice approximation? Let us say that the center of the balls must lie in a lattice, but to make it a bit more like the continuum case, let's say that the balls have a very large radius. So they are non-overlapping large balls with centers on the lattice. And they want to know how does it behave at high fugacity. Actually, what might be more relevant to this packing of balls may be intermediate fugacity, but it's a good start with the high fugacity regime. And as we saw in the Brushin's proof, it's very relevant to understand first the maximal density packings. So Mazel, Shtul, and Sukhov on the square lattice and hexagonal and triangular lattice completely described the maximal density periodic packings for all the values of the radius. And they found that there are, for all but finitely many radii R, there is only finitely many maximal density periodic packings. And in those cases, when there is only finitely many ways to pack the system at the maximal density, then they proved the analog of the Brushin's result. That is that your system in a high fugacity regime will resemble one of these maximal density packings at most places. So it is a crystal in the sense of these definitions I gave earlier. It is not a liquid crystal, it's not nematic, it's really a crystal, just resembling this maximal density packings. However, they also found that there is finitely many exceptional R's for which the maximal density packing is highly non-unique. Here is an example. When you pack squares on a lattice, you can reach a full covering of the lattice. The center of these squares is on the lattice. You can certainly reach a complete covering of the entire space with squares on a lattice, but there are many, many ways to do that. You can slide the columns. So you take a full column like that, and you can slide it with respect to the adjacent columns, and in this way obtain a new packing. You can either slide the columns or you can slide the rows, but you cannot slide both columns and rows. Once you've slided the column, then the rows are obstructed. You cannot slide them anymore. So I hope you get some picture of how you pack squares on the lattice. This great degeneracy of maximal packings, the fact that there are so many, prevented the proof of Mazel-Stuhl-Suchov. They actually conjectured that it prevents long-range order in this system at high fugacity. In the last few minutes, I mentioned a recent result of myself with my student Daniel Hadass. We studied this model, one of the cases of Mazel-Stuhl-Suchov, maybe the simplest case of that they were studying, where the basic tile is a 2x2 square with a center on the square lattice, like so. And we wanted to understand the high density, the high fugacity regime. I'm not going to go into that because of lack of time, but I'll just give you some picture. So how to reach this type of picture. So maybe I'll also give some conclusion. We found eventually that the conjecture of Mazel-Stuhl-Suchov does not hold in this particular case, that the system does display order at high fugacity, but the order is a columnar order. You can kind of see it in this picture. Most of the tiles arranged in a column, in columns like that. There are a few tiles which violate the columnar order, but the system has no translation. It has all of the translations in the up-down direction. It doesn't have all translation in the right-left direction, because if you shift this square by half a square, by one lattice side, which means half a square to the right, then you'll get a different packing. So it's not invariant to translations in the right-left direction, but it is invariant in the up-down direction, and it does break the rotational symmetry because of that. So this is it's reasonable to call this columnar. Usually the word columnar is in 3 dimensions, but you can use it also in 2 dimensions, and people have used it. And let me just give some intuition for this. To get this idea, to get an idea of what's happening, it's again reasonable to look at the maximal density packings, which look maybe like that. But here, by the way, the colors in the picture are the parity of the center. So the x-coordinate can be either even or odd, and the y-coordinate of the center can be either even or odd. So this gives you 4 types of tiles. In a fully packed state, 2 of these types are absent. So you just see all of the x-coordinates even, say. Now, what we see is that it is no longer true, not unlike the Brushin, that the high fugacity regime equals the maximal packing at most places. It is no longer true, because even if there are some long columns which equal the maximal packing for a while, then eventually they must terminate at a gap, and when they terminate at a gap, then they shift. So the column is never with the same y-coordinate parity to infinity, but has many gaps along the way. So the right intermediate model to compare to is this one, where you force all the columns to have an even x-coordinate. They're really just independent, but you add the gaps as needed. So it's really a union of one-dimensional models in this picture. And what we prove, roughly speaking, is that the actual system equals this type of distribution. There is a coupling where they're equal at most places, roughly speaking. We don't say it exactly in these words. Okay, so I don't know, maybe you understood this last slide or maybe not. Here is a rigorous statement, but this is really mostly for the experts, that we prove that there are these many Gibbs measures. Every periodic Gibbs measure is a mixture of 4 measures, but the particular one is invariant for 2z and z, and is extremal, and the tiles mostly prefer to see, say, an odd center of their x coordinate, and there is fast correlation decay, but with different rates in the different directions. So I don't go into that. This is too technical, and we don't have the time. And also, still for the experts, we also established a version of the chessboard estimate for periodic Gibbs measures. This could be useful in other contexts too. In any case, so this is really a slide for experts. I don't expect you to follow it. Let me end my talk with a list of open questions. So what would be good to prove? The most pressing issue is the issue of continuous symmetry breaking. For instance, to study the packing of balls in RD, how do they look? The high fugacity regime of balls in 3 dimensions. Recently, we understand the maximal density packings of balls in 8 and 24 dimensions. You can also try it there. What is the, pack 99% of the maximal density of balls in 24 dimensions? Does it look more or less like the maximal density, like the Leach lattice everywhere? Does it have long-range order? This is open as far as I know. Certainly, it is open in 3 dimensions. And in 2 dimensions, I told you it should look a bit different. It should be a nematic phase. Or if you will, you can try to establish on Zager's conjecture to study long rods in RD. So these are all about continuous symmetry breaking. These are the most pressing issues. We studied the 2 by 2 squares. You can try to study higher dimensions, larger cubes. We use the so-called chessboard estimate, reflection positivity. So our method would not exactly work for all of them, although there may be extensions. So I don't go into that, but this is another thing you might try. And finally, the physics predictions are very elaborate. Physics or other sciences, they tell you also the critical behavior exactly at the transition points between the two, the ordered and the disordered phases. What happens exactly at the critical fugacity, and we don't have any ways to approach that. Okay, thank you very much.
Let's thank Ron for the wonderful talk. So I open the floor for questions.
Could you please, I don't remember if you mentioned what exactly was the value of the critical lambda?
I didn't mention, but the model is defined with this Fugacity parameter. You can instead, if you wish, talk about the density parameter. It should be similar. So I told you that if you have a low density of tiles, then the system should be disordered. The high density or the intermediate densities are less clear, and there could be many types of behavior. Let me show it, for instance, in this picture. In here, in intermediate density, you should see this kind of behavior, and at high density, something else. But then you can try, to tune your density, tune it exactly to the number, I don't know, 0.78 density, exactly to the number where the behavior shifts from one to the other. And the physics predictions are that there will be an exact number, a specific density where you shift the behavior. That density is called the critical density, and there is an analog of a critical fugacity in this fugacity parameterization. And the question is, well, how will the system look like in exactly the critical point? The physicists talk about the phase transition, the critical behavior. The 2 usual possibilities, and sometimes there are more options, are either that you see coexistence, meaning with probability, say 1/2, you see a picture that looks like this, and with probability 1/2, you see a picture that looks like that. If there is coexistence, the physicists say that this is a first-order phase transition, but it could be even more interesting that there is some kind of continuous way in which this deforms into that. In this case, you sometimes see scale invariance, conformal invariance, very interesting things. which are neither this phase nor that phase, but rather something intermediate, fractal behavior usually. And this is called the second order phase transition. So the physicists say that in some of these systems you should see second order, some you should see first order. They even analyze the critical behavior more precisely, but the mathematicians don't know to say anything about that for these systems.
I see. Thank you.
Sure.
Are there other questions from the audience? So actually on this slide, so no, on slide number 5,
Yeah.
Do we understand precisely what happens at maximal density for these rods? So you have long columns.
Right.
So do we understand what are the uniform Gibbs measures? Is this already well studied?
You mean for the maximal packing? So you want a full covering of the
Yeah, full
lattice,
covering, yes.
length 7. So we don't understand, and probably this is a key to understanding the high density phase.
So
There
I remember some work by Martin Tassi about this, but yeah, I will try to look up the references. And
I would be very interested if there's
So-
something. Right. I remember, right, with Rick Canyon he was studying, but maybe it was not very long rods, but maybe it was 3x2 or something, 3x1.
So
I think.
what I remember is there is a height function representation for some of these, and they were proving a variational principle for and some form of LDP, but I don't remember how strong were the results.
That's very interesting. Thanks, Nishant. I should look into that. I forgot this, and it might be relevant. Let me mention though that something about the entropy is proven, I think, by Dar and Rajas, if I'm not mistaken, but also before that by others. I mean, they maybe one proved the lower bound and the other matching upper bound. So at least in the limit, as the length of the rods, which is here 7, tends to infinity, then the entropy of maximal coverings, when you cover all the lattice, is known, at least in the limit, I think.
But what does that mean?
Structure. Yeah.
What does that mean? That you're taking the length of the rod going to infinity. How do you scale this?
I think if I recall correctly, okay, I haven't looked at it sufficiently well, but I think what you do, you look at say this, you look at z squared. This is on the z squared lattice. You look at so maybe you take a big domain in z squared. You ask how many ways are there to fully cover it. So maybe it matters how the shape of the domain is, but they pick what is relevant. You ask how many ways. You take the log of that. You divide by the volume, and you get the a number like the entropy per site.
Sure.
You take the volume to infinity. That's your entropy per site in the infinite system. And now you look at the asymptotics of that as the length of the rod goes to infinity. And I think the asymptotics is understood even with the leading constant.
I see. Okay. And like this is some precise number that they give, or precise expression, I guess.
So I don't remember the number. I think it involves E, for instance, natural basis, but beyond that, I don't remember. Right, and so this is intimately tied to the structure, and these kind of degrees of freedom play a role in determining how many options you have.
Can you go a few slides towards the end? You were talking about, let me see which slide was it. I've written it down. Yeah, so the previous slide before this.
Yes.
Right. So, so you're somehow looking at some, if I can sort of reformulate this question, can I think of it in this sense that you have some subset of Z2, which is finite, and you're looking at tilings by this such that fewest gaps sort of it covers as much of Z2 as possible when you translate it by that set. This is in some sense what you would think of a maximal density packing.
It's a periodic packing, so it's even easier. You can ask about periodic placements of tiles, and every periodic placement of tile will have a well-defined density, which just means how the fraction of sites that are covered from the lattice by amenability. So you can really talk about the maximal density which is achieved by periodic packings. I guess when I say it now that you might worry that if you increase the periodicity, you may cover more and more, but I think maybe they understand that this is not what's happening in these cases.
So,
finite any exceptional one.
Right. So this is also actually quite related to some questions that were recently answered by Greenfield and Tao. I will forward you some references.
By whom again?
So there's this question which you might have heard about called the monotyling conjecture, which says the following: that if you have a single tile and suppose it tiles Z2, then essentially all tilings look somewhat periodic.
Okay. Yes.
And now you can ask similar questions where instead of tiling, you have a K covering of the Z2 lattice. Now, if you have a maximal tiling of this maximum packing of this sort, then if you translate it, then you can imagine that you're essentially getting some form of K covering of the lattice. And it seems to be related, probably, maybe not, but yeah.
Sounds interesting. Yes, I'm not so aware of this literature, so I'll be happy if you can forward it to me and I can look. Right. Right.
Can I ask one more question, please?
Sure.
So you only talked about Z2 lattice. Is there any some difference if I look at the triangulation or some sort of hexagonal lattice?
Certainly. So if you consider packings on the, in this case, it's the hexagonal lattice, then the maximal density packings are different. They depend on the specific lattice that you've chosen. And in this work of Mazel, Shtul, and Sukhov, they understand both the square lattice, the hexagonal, and the triangular lattice. So it's very comprehensive. And moreover, the phenomena that we have been describing here, that we said that there is columnar order, we're not quite sure that this kind of order will always hold. So maybe on the hexagonal or triangular lattice, we might have more kind of sliding or other degrees of freedom in the maximal packing that may indeed impact the Gibbs measures or the structure, the long-range order. So it is not, although with this particular model we proved that there is columnar order, I'm not claiming that in all cases there is such a columnar order, and it may be that the lattice structure specific tile affects this. Certainly, the analysis is different, and the outcome could or may not be different if you take a different lattice, and it's interesting to try that.
I see. So going back to the first question that I had asked about the existence of a disk at the center, given the boundary. Yes. So you said that it is that probability is invariant when the lambda is very large. Invariant of the size.
In this, it's this one, right? So the probability that the center is occupied will be something like e to the minus, I don't know, e to the minus lambda, let's say, e to the minus constant lambda, something of that nature when lambda.
I see. Okay. So I was just trying to see, like, is there any, like at the story level or at a heuristic level, is there any connection between this this work, which is, they often talk about rigidity of random points, like random point process,
right?
Wherein they fix the fix the boundary, and then they talk about different point prices, for example, determinantal and permanental point prices, and then the depending on the correlation decay, like the parameter of the correlation decay will determine the rigidity.
Right.
So here again, you are saying that that fugacity is related to the density. So I mean, the questions can be asked in terms of the density instead, like just changing the language. So is there any such connection?
I don't know that there is so much a connection. If I fix a domain and I tell you how many points I put in that domain, so I fix the density, well, then that's rigid with respect to the density because you always get the same number of points inside. But locations are not rigid. I mean, they somehow try to use their degrees of freedom, and there will be these defects, although most locations will be, say, on the even lattice, but there will be a few defects occasionally that are on the odd lattice. So unless you're really in the maximal density, in which case it will just be a single specific packing, which is the best one and nothing more, in this case of crystal order. So I don't know that these are really the same questions. Usually they study different point processes there. I don't know. I haven't tried. So maybe there is.
No. I'm just. This is a wild question.
Yeah, I understand. I might be missing though because I haven't thought about that. So it may be that if you think about it, you can find questions in the intersection. But largely these are disjoint topics for now.
I see. Okay.
They usually talk about different point processes and they want to understand the properties of these point processes. And here, we also want to understand the properties, but I think it's a different point of view. It's a good point. I haven't thought about the possibilities to put these ideas together.
Okay, thanks, Ron.
So we have already asked quite a few questions, but Ron, actually, before I should ask a question, maybe I should ask others if they want to ask a question.
I was actually just wondering in that the rods, the graph, I think the previous slide itself.
Yes, maybe
fix the boundary.
Just a minute, let me put it up. Sorry. Would you want this one or the next?
The one with the, I think the HDD packing.
This one? Or,
yes, this one.
Oh, okay, this one. Yes, so
what happens if you fix the boundary?
This is somehow part of the question. So as we saw in the case of the result on the nearest neighbor hardcore model, if you fix the boundary to be even occupied, then this even order goes all the way to the center. If you fix the boundary to be odd occupied, then by symmetry, the odd order goes all the way to the center. Somehow, really, this is the question that we are trying to approach here, whether there are ways to fix the boundary so that a certain order permeates the system. This is like a different phrasing of the main question that we're interested in. For instance, in this nematic phase, it stands to reason. I don't know if that's exactly, maybe it's not exactly what's been proven, but it stands to reason that if you fix on the boundary the rods to be horizontal, maybe in a certain way, then indeed you will force the system to mostly have horizontal rods. If, on the other hand, you try to do the same thing here, then maybe you will no longer do it because here the system doesn't actually have a preferred orientation. But maybe you didn't know that a priori, so you could try to fix and just see what happens. So indeed, these phases, the different phases of the system, are characterized by the response of the system to the fixing of boundary conditions. And this is a different way to phrase the main questions that we're interested in. When we ask how does the system order it, you can ask it in terms of the boundary. And let me add here that it's not at all obvious what are, a priori, what are the right ways to fix the boundary. Maybe you have one way in mind. Maybe you say, okay, fix all the horizontal rods in the boundary. But it's not clear that this was the right thing to do. Maybe you should instead have fixed it differently. Maybe you should have left some degree of freedom to the system to say there exists a rod, but they don't say exactly where it is. So it could still have some freedom left and right. It's not at all obvious a priori how you should fix the boundary. And it's very interesting to study the response of the system.
All right, thanks.
Sure.
Are there other questions from the audience? So, Ron, just one last question maybe from me.
Sure. Yeah, please.
So in your results about tilings by 2x2 boxes, so you stated your results for Z2, I think, for so particular reason. Do you have a sense of what happens in Z3 or higher dimensions, or do you have no guesses at all? Do you have any results?
I can guess for the cases of cubes in ZD. So maybe you can ask about more general models with the sliding phenomena, but let me only talk about cubes in ZD. So when you talk about cubes in ZD in the high fugacity regime, then I expect you would still see the same type of columnar order, no matter what is the side length of the cube, so long as it's at least 2 and the dimension is at least 2. So it will be similar type of thing, and that means you will have dk to the d-1 periodic and extremal Gibbs state. I don't know exactly how to explain that. You want to choose, you have your cube. In the side of the cube, you want to choose like a single point on the side, which will be your translation. And then you want to orient all the cubes in rows in a certain direction. So the D factor accounts for the directions that you can orient. So the D factor is the directions which the system could orient by. And the k to the d-1 is the shifts once you've chosen the direction. So I expect that's my guess at the moment that this will happen. Our proof does not establish that because first of all, we only work in 2 dimensions and you will need more involved arguments in higher dimensions.
So I'm sort of curious. I'm just thinking about k equal to 2, and as you also noted in the slide, for k equal to 2, it's reflection. So there's reflection positivity in all dimensions. So
yes,
so what is special about dimensions here?
I mean, this has something to do with the proof method that I didn't say anything about, but I can open briefly some slides. You want to show that interface regions between vertical and horizontal configurations are rare. So what we do, we define this notion of sticks, which has to do with whenever tiles of different parity touch each other, then you have a stickage, and we study these sticks and the way that they enter the system. And if you wanted to have a 3-dimensional notion, then you would have to think what would be an analog. It could be just as simple as saying cubes of different parity, but maybe because now you have more options for how they touch, and maybe you have to think a bit more. So our main lemma has to do with the question of whether a stick crosses a square. If you're in 3 dimensions, you will need to find the proper generalization of that. I'm not saying it's hopeless. It may well be that you can somehow do it, but it's not immediate from what we do. You'd have to work to understand what to do. Still, I expect it, and it may be that you can. So I'm not ruling it out, but it would require more work.
That's very interesting because again, in this other literature, which I was talking about, proof techniques fail completely in 3 dimensions almost immediately. Nobody knows what is going on. But I think the nature of problem is different in both cases, from at least what I've understood from your from sketch.
It may be that we use some version of a Pyre's argument eventually.
Yeah.
It's interesting because we establish a columnar order. I didn't say, by the way, but this might be the first work in mathematical literature to establish a columnar order. So we use a Pyre's argument. The argument should be adapted to the phenomena that you expect to see. I am not sure if you have a columnar or nematic or disorder or whatever in the other systems that you care about. For cubes, we expect columnar order, and the methods could be relevant. I'm not sure in what Martin was looking at, whether you have or don't columnar order. In these rods on the lattice,
I don't think he established anything like that. Yes, I think what he did establish is a large deviations principle. So he had a height function, and at least this is what he wanted to prove. This is what I remember, but whether he actually achieved it or not, this I'll have to look at his paper again.
Okay, yeah, I'd also be interested. If you have a good reference to send me, I'd be very interested to look, or maybe I'll look myself. But if you find, I'll be happy to understand. I'll just mention that this is not by accident that the rods here have length 7. The phenomena of a intermediate density nematic phase is predicted not to occur for rods of shorter length. So even length 6 is not enough. It's supposedly happening starting from length 7.
I see.
So it matters a lot whether your tiles, have this shape or that shape or this shape, or every little change might change the results. So you have to be a bit more specific. Also, we studied 2x2 tiles. What about 2x1? Well, 2x1, these are the dimer models. They're always disordered. So it's completely different.
So just to, maybe I should stop recording before I say more.